All right, so here is a Faraday's law problem, Faraday's law of induction, and it states to consider a rod of length L that is forced to move at constant speed v along horizontal rails. The rod, rails, and connecting strip form a conducting loop. The rod has resistance R. The rest of the loop has negligible resistance. A current I flows through the long straight wire at distance A from the loop and set up a non-uniform magnetic field through the loop. Now the question is asking, mainly, to find the magnetic and direction of the induced current in the loop in terms of given parameters. Now, how do we start this? So the first thing we have to recognize is that this is a non-uniform magnetic field through the loop. And that means that the magnetic field shared in this entire diagram right here is not uniform, So one thing we can notice is that the magnetic, well, this is going inside the page, and this is going outside the page. All right, so how can we start this? Well, the first thing we can do is set up the equations that we need. So the thing we're going to need is first the derivation of the Biot-Savart law. Now, the Biot-Savart law states that dB equals mu naught 4 pi times I infinitesimal s r of r squared. Now, this is the Biot-Savart law in general, but we're not going to be using that law. We're using a derivation of the Biot-Savart law, and that is going to be the B for finding the magnetic field for a long straight wire. So that's going to be B equals mu naught I 2 pi r. This equation is what we're going to start off with. All right, so let's get started. All right, so the first thing we're going to do is, based on the equation that we wrote, we have to find, I don't know why I erased that, I should have left it there. B equals mu naught I 2 pi r. Now this is to find the magnetic field for the wire. Now, if you look at the question, we see that there are no numbers. No numbers, no nothing. So we can immediately surmise that this is a symbolic question that we're going to be using. So basically that means we already have B right here. So we can move on. Very convenient. So the next thing we can do is to find the magnetic flux. Now the magnetic flux equation is the integral from B dA. Not from B dA, sorry, integral of B dA. Excuse me. Now, this right here is the general equation of the magnetic flux. Now we have to specifically modify the equation for this occasion, for this problem's occasion. Now, how can we do that? Well, first thing we can look at is that a current I flows through the long straight wire at distance A from the loop and sets up a non-uniform magnetic field through the loop. That's one important detail. And to consider a rod length L that is forced to move at constant speed V along horizontal rails. Now we can see that current I right here, moving to the left, is basically carrying the current through the wire. Yeah, hence. And now we can see that the distance from the wire itself all the way down to the bottom of L is going to be L plus A. Now, yes, technically the magnetic or the current wire is closest with A right here. So you could be saying, well, why can't we just do A? Why can't we just do A? Instead of just going to the hassle of, all the way down here. You know what? I keep forgetting that this thing has a laser pointer. All the way down here. Why can't we just do that? Or just here, right here? Why do we have to take into account all the way right here? That's a good question. So the thing for that is how magnetic fields act in this context of the problem is that it goes in a loop. it behaves in a loop. So given that the wire is moving at a constant speed v along the horizontal axis, taking into account L takes into account everything in here, the entirety of the loop, not just A. So that's why we're doing that. So that being said, we can modify the equation to take the integral from A to A plus L. And now we're going to do from B with respect to R. Now R is the distance, taking into account the, well, let's elaborate it, dr. Now dr right here is what we're going to be integrating with respect to, and dr is basically the universal denotation of the infinitesimal change in variable distance r. Now, why we don't do a is that a is just a fixed distance. It's not an infinitesimal, it's just a. And it's a fixed distance, so it's not going to move, it's not going to change, it's fixed always. So that's why we use BR with respect to R, sorry. Right, now we can move. Oops. Yes, I do write over some of the questions so I can leave a lot of space. Oh, I just made it worse. Just like that, there we go. All right, so BR times X dr. All right, why is my tablet not responding? Hello? X, oh, there we go. Woo. X dr. And the reason we use X is because the elemental should be X because X is the horizontal length, which is changed in related to V, wherein V equals dx over dt. All right, so now we can move on. And what we can do next is that since this is BR times X dr, we can then replace B with the given wire, or the value right here. So that's going to be from integral A plus L of mu naught I 2 pi r x dr. All right, now we can move on to the next step. Now that's going to be mu naught. Now let's bring the constants forward. 2 pi A plus L of, since we're moving the constants in front, but it's integrating with respect to R, we're going to leave the R right where it is in front of, or behind the integral. So that's going to equal 1 over R dr. Oh my goodness, I forgot the X. 2 pi x. All right. Now, if we move on, it's going to be mu naught I x. I wonder why I put y there. Mu naught I x over 2 pi equals ln of r of integral, oh, not integral, we already did that, so then that moves on to ix 2 pi, and according to the integral, we're going to simplify this to ln a plus L minus ln of a. And with the integral rule, after we simplify it, or the natural logarithm rule, this turns into a plus L over a. And this is going to be the magnetic flux right here. Now we set it up. Now what can we do with it? Now, if you know the Faraday's law of induction equation, that's going to be negative d magnetic flux d phi dt. d phi dt. There we go. Now we can use this equation right here. So if you plug in phi, or the magnetic flux, we get mu naught Ix over 2 pi ln of A plus, now instead of x, it's going to be Vt. I believe I wrote L last time. Sorry about that. X. Not sure why I keep writing L. It is length, but X, there we go. Sorry about that. Now, X does equal Vt, so we're going to leave it as X. All right, where was I? A. Right, so as you can see right here, just keep in progress. And that is going to turn into mu naught Ix 2 pi negative dt. Since we're moving the constant in front, this guy right here, of ln A plus Vt over A. Now we can simplify this. And if you know the rule of natural logarithms and how they behave, you can write this as I wrote L again. Oh, geez. Come on. Of 2 pi ddt. Now, if you know how they act, you can write it the same as this. Now, what we first need to know is that A right here is a constant. See? At a wire distance A right here. Now that implies that A is a constant. It's just a number. There's no variables attached to it. So we can safely say that a derivative of a constant is going to turn into 0. Now we're going to move on. Again, mu naught Ix over 2 pi. And after you derivate a natural logarithm of A plus Vt, that's going to equal 1 over A plus Vt times the derivative of, using the chain rule, A plus Vt minus the constant 0 that we just did, this guy right here. All right, so now we can move on. Again, Ix 2 pi 1 over A plus Vt times 0. And now according to the chain rule that we did right here, A again is going to turn to 0 because the derivative of constant is 0. And now we can look at the variable right here. Now V also is a constant right here according to the problem, but T is not a constant. T is a variable, which is time. So a constant with a variable attached to it, the derivative is simply going to turn into, well, this guy's going to turn into 1, which makes it just V itself. So plus V, let's write that better, V1 equals 0. Now if you simplify this is simply going to turn into mu naught Ix 2 pi times 1 over A plus Vt times V. If you simplify that again, it's going to be mu naught Ix 2 pi times V over A plus Vt. And there you have it. This is the induced EMF. EMF. Induced EMF, Faraday's law of induction. Right. Are we done yet? No, unfortunately not. But we are close. So once we have the induced EMF, we can then find the induced current by using Ohm's law. Now Ohm's law, the standard version, is V equals IR. Potential equals current times resistance. Now we can do a little bit of algebra and leave induced current by itself. So that's going to equal, it's going to equal V over R. But, well, we can't do that. Oh, well, this is not the correct form, I should say, because we're looking for the induced current, and we do have the induced EMF. Now, V is going to act as the induced EMF in this context. So it's going to be I equals induced EMF over R. Now, that's going to be Ohm's law in this context right here. So all we need to do is simply plug in, because I equals this guy right here, and that's going to be negative, negative mu naught I x v 2 pi a plus v t. For those following, I just multiplied simply these two together into one fraction. Now that's going to be over the resistance R, and that will simply turn into mu naught I x v over 2 pi r a plus vt. All right, now there you have it. This is the induced current. Now we have one answer down that they're asking right here. They want the induced current. Now, aside from the induced current that they're asking, we also need to find the direction. Where does it say that? Yes, direction right here. And to find the direction, we have to use something called Lenz's law. Now, oops, it is not working. Okay. Some trouble with my tablet right here today. All right, so Lenz's law right here basically states that the current induced in a circuit due to a change in a magnetic field is directed to oppose the change in flux to exert a mechanical force which opposes the motion. Now, to simply determine that, it's actually pretty simple. So if you look at the diagram right here, just use a laser right here. If you know how to use the curl right hand rule, simply point your thumb to where the current is flowing. So in this case, the current is flowing leftward. And since this is an X, that means that the magnetic field is curling inward. So if you point your thumb to the left and curl your fingers, that's going to mean that the direction of your finger that's curling is going to be counterclockwise. So the finger curling is counterclockwise at I going left. Right now, based on what Lenz said, we're going to do completely the opposite of that. So if it's going opposite of that, I is going rightward, which means that the shouldn't have done that. The magnetic field is going clockwise. All right, now there you have it. So this right here is the induced current, and the induced current is going rightward, or at clockwise. The magnetic field is going clockwise. All right, there you have it.